So, in today's lesson, we are looking at the final part of the nephron and how the body can reabsorb or not reabsorb water depending on the internal conditions. So, we've looked at the kidney. We're going to talk about this bit today. So, we're going to talk about the osmoreceptors in the hypothalamus and talk a little bit more about the posterior pituitary gland. Okay, so this is what we've looked at so far. So this is the loop of Henle. So up here we had glomerulus, where we had ultrafiltration, proximal convoluted tubule, reabsorption, and last lesson we were looking at this situation here. So this is the loop of Henle. So if you remember, the ascending loop actively pumps out sodium chloride ions. That lowers the water potential in the region between the loops of Henle. Water then moves out from the descending limb while sodium and chloride ions move in. So we end up with our most concentrated urine down here at the bottom. The concentration then decreases because the sodium chloride ions are coming out, but the water isn't. And then we talked a little bit about the distal convoluted tubule adjusting the concentration of ions. So what we're going to focus on today is the collecting duct. Now, as I said on many occasions, there are about a million nephrons, but there aren't a million collecting ducts because more than one nephron connects to one collecting duct. So basically what this means is that within the medulla of the kidney, you have got lots and lots of collecting ducts, lots and lots of loops of Henle, all packed really, really close together. So anything that affects this area here is going to affect what's going on in the loop of Henle as well as in the collecting duct. Now, we talked about how the descending limb is free permeable to water and the ascending limb is not. But what is different about the collecting duct is that the collecting duct can change its permeability depending on the conditions within the body. And that is what we are going to look at today. So if you have drunk a lot of water and you don't want to keep it, they become less permeable and out goes that water. If you haven't drunk a lot of water, or you've been doing a lot of exercise, a lot of sweating, you've been losing water in other ways, then they can become more permeable to water, and water will be reabsorbed back into the medulla and then from there into the blood capillaries and off around the body. So this is a homeostatic mechanism, sometimes called osmoregulation. Osmo is anything to do with water. And it's an example of negative feedback. Now we're going to look at negative feedback. At one point we are going to look at positive feedback as well, but negative feedback is by far and away the most common homeostatic mechanism within the body. So in the brain, in the hypothalamus, which is the part of the brain right in the middle, you have a location of your osmoreceptors. Osmoreceptors are basically monitoring the water potential of the blood. Then you have these effectors, cells in the posterior pituitary gland, and they change the production of the hormone ADH, which stands for antidiuretic hormone. So what does ADH do? Well, you have to first of all understand what diuresis is. You probably know what a diuretic is. A diuretic makes you wee a lot. So diuresis is the production of large amounts of dilute urine. You usually do that if you've drunk a lot of water, although there are some chemicals that are diuretics. Caffeine is a diuretic, alcohol is a diuretic, but diuresis is the production of large amounts of dilute urine. So ADH is antidiuretic hormone. It doesn't want you to do this. It stops you losing too much water in times when the blood water content is low. Okay, so ADH is a hormone that stops you losing too much water. And it's produced in the posterior pituitary. This is the pituitary gland here. Okay, this is the pituitary gland, this is the hypothalamus. And this, you have the anterior pituitary and the posterior. So the anterior is like at the front, so like your nose will be here, and the posterior is at the back. Now they work in two different ways. The hypothalamus and the posterior pituitary are connected by these neurosecretory cells. So the hypothalamus detects the concentration of water, the water potential of blood, These cells, which are effectively neurons, they produce ADH. It passes along the axon, where it's then released into the blood, and from the blood it passes off around the body. Now, other hormones produced excuse me, by this are oxytocin, which is involved in birth, so it helps the uterine muscles contract. Okay, and ADH, which we're looking at today. Now, your anterior pituitary works in a slightly different way. You have these cells up in the hypothalamus detect various things. They produce secretory hormones, which then pass down to this one, which causes these to secrete other hormones. Okay, but we'll worry about that a bit later on. Right, so ADH. Basically, what happens if the water content of your blood is detected to be low? Excuse me. The pituitary gland produces and releases ADH. This travels to the kidney in the blood, and basically what it does is it has an effect on the permeability of the collecting ducts. So this is a cell that lines the collecting ducts. So this is a cell that lines the collecting duct. This is the collecting duct. This is the blood vessels. So we have a situation where within these cells we have these little vesicles called aquaporins. And basically they're like little tiny vesicles, little tiny balls, and within them they've got protein channels which allow water to pass through. And they can either be within the cell and not doing their job, or they can be fused with the membrane on the side of the collecting duct closest to the lumen. So what happens is ADH comes along. Now ADH is a peptide hormone, so therefore doesn't enter the cell. So it binds to the receptors. Remember, those receptors are either glycolipids or glycoproteins. They're complementary to the hormone, and they bind to that. That then sets up a series of enzyme-controlled reactions, which ultimately ends up activating a phosphorylase enzyme. That causes vesicles, these aquaporins, to move to this side of the cell and to bind, so to fuse with the membrane, because remember they're vesicles, so they're also made of membrane. They fuse with the membrane over here, and now we have lots more water channels in this side of the cell. So they fuse with the cell surface membrane. Okay, and then the water molecules will now be moving down the water potential gradient. There'll be a higher concentration of water in here than there will be in here. So we'll move down the water potential gradient to an area that's more negative. And basically, they go back into the blood. Now, if you continue to produce ADH because it's a hot day and you've been sweating and you've been exercising, then these aquaporins will stay here and they will keep reabsorbing water, and ADH will constantly be being produced. As soon as that ADH stops being produced, or levels get lower, then this will not happen anymore. The ADH won't bind to the receptors in the plasma membrane. These processes essentially will be reversed, and the aquaporins will be remade. Okay, right, I'm going to watch a video. Hopefully.
What happens in your body when you start getting dehydrated? Water levels in the blood decrease, and this is detected by receptors on cells in the hypothalamus. These receptors are called osmoreceptors. In response, the cells secrete the signalling molecule antidiuretic hormone, or ADH. ADH is a hydrophilic peptide hormone. The ADH is released from the pituitary and travels in the blood to the kidneys, where urine is produced. Nephrons in the kidney filter urea, salts and other solutes out of the blood. The last part of the nephron, the collecting duct, is the final place the body can reabsorb water. ADH receptors are located on cells lining the collecting duct. ADH binding to its receptor triggers a cascade of interactions between molecules inside the cell. This process is called signal transduction. It activates vesicles containing water channels called aquaporins. These are inserted into the plasma membrane. More water can now move from the collecting duct back into the blood. Because of ADH, less water ends up in the urine and the urine becomes more concentrated. So if you are dehydrated, ADH helps you to conserve water by decreasing your urine production.
Hopefully that just clarified a few points I've been over. So the water moves easily up the collecting duct as it moves down the water potential gradient. And then this was caused by the active pumping out of sodium ions from the descending lip of Henle. So your medulla has got a lower water potential now because we put all those sodium ions in there from pumping out from the lip of Henle. And as I said, they're all very closely related to each other. Now, also the other thing that happens is your hypothalamus sends a message to your thirst centre of your brain and makes you feel thirsty, and then you start to drink. And then basically what will happen then is your ADH levels will slow down, you won't produce as much ADH because your osmoreceptors detectable potential for blood has got back to normal. The collecting ducts are now less permeable to water because those aquaporins now reform, and so that takes about 10 to 15 minutes from your body recognising that you are lacking in water to put all this in place and reabsorbing the water. Okay, so hopefully that made sense. All right, so that's what happens in the collecting duct and the mode of action of ADH.